This is the BBC.
This is Under the Weather from the BBC.
With me, Claire Nazir, and Simon King.
In this podcast, we'll be joined by a range of experts as we answer some of weather's most interesting and challenging questions. In this episode, why does the jet stream rule our weather?
We blame the jet stream on everything that happens for the UK weather. We blame it on floods, rain, Arctic blasts, heat wave, you name it. It's all down to the jet stream.
I'm going to go right back to basics here. Why do we even have the weather on planet Earth? Let's think about the Earth and the Sun. They're 93 million miles away from each other. Now, I'm going to replace my sun with a torch, and imagine I've got my Earth here like a big ball. Okay, my torch is shining to the centre of my Earth. Okay, so I think that's where the tropics are. So you've got more heat, more energy concentrated on the tropics than you do at the poles. And that's why there's that difference in temperature with the hot air by the equator, the cold air by the poles. Now, nature doesn't like that imbalance, so it wants to kind of correct itself. So we need a format, a way of transferring that heat from the equator to the poles. Now, the way we do that is with the warm air at the equator rising. It hits the top of the troposphere and it has to go somewhere. And the only way it can go really is north and south towards the poles. So it's travelling along and then it cools and then it sinks. It goes back down to Earth. And that process happens again. It's got to go somewhere. So that air is going north and south once again. And then you've got that circulation. You've got a cell that has developed near the equator, moving its way further towards the pole. And that's our first cell. That's the Hadley cell. Now that process continues, and then you have the feral cell and then the polar cell. So there are three different cells.
So where the air rises, you get cloud and rain. Mm-hmm. And where it descends, you get pretty much desert or dry conditions. And you can see that, can't you? If you look at a globe, you can see where the wet weather is. You can see where the dry conditions are.
That's why we have the Saharan desert. The plains across the United States, that's why they're so dry, because you've got that air which is tending to sink down.
And where we live, in the mid-latitudes, we get a lot of rain.
Absolutely. So how does the jet stream form out of this? Well, the boundary at which these two cells meet each other high up in the atmosphere, well, it's quite complicated. So I'm going to break it down, not talk about too much about the dynamics of it, but the simplified version is that as those two cells meet high up in the atmosphere, near the troposphere, you get a strong temperature contrast. And that causes a dramatic increase in the wind speed. So at 6 to 9 miles high up in the atmosphere, the winds are their strongest. And that's this core of strong winds of about 140 to 220 miles an hour. And that is known as the jet stream. And that jet travels all around the Earth. And you have three of them. You have the polar front jet, which is where we are. You have the subtropical jet, which is around about where the Mediterranean is. And you have another one, which is the African easterly jet. It doesn't work in quite the same way. It's much lower down, but it's important to the global weather. So, Claire, I think we should talk more about the polar front jet then. That's the one that impacts our weather the most.
In a nutshell, you've already said it's the difference, the battleground between the cold air from the poles and the warm air moving north from the equator. And this is where it hits. It hits 6 to 8 miles up high. So you would think it's detached from what's happening down at the surface, but we'll learn it actually isn't at all. It's all connected. And this jet stream is part of collectively what we call Rossby waves, which circle around the globe at around the mid-latitudes. And imagine the mid-latitudes, that's where we live, 30 to 60 degrees north. It's where we have seasons, we have rain, but we have dry weather as well. It's never too cold, it's never too hot. We don't tend to have deserts, we don't tend to have tropical rainforests. It's a nice balance and where we can live a good life, weather-wise. The land is very fertile. There's lots of vegetation. So this is where the weather happens. And it's not just where we live across Europe, other parts of the world which are in the mid-latitudes as well. But
and they're all impacted by the jet stream.
Jet stream as well, different jet streams which happen in the Pacific, etc. It's all connected. So where we are, we really look to the west to see where our weather's coming from most of the time. And the jet stream does a number of things. So let's talk about the jet stream in terms of its position relative to the UK, the shape of the jet stream, and how strong the winds are within the jet. So you imagine the jet stream is a really fast-moving band of air, miles high, almost like water going through a hose. So it's really accelerating through that hose. And then sometimes there's little kinks in that hose as well. So it's not always just a straight line of winds. Sometimes that wind kinks. It goes further south, goes further north. And what we find, where we see those kinks in the jet stream going further north, below that we see high pressure at the surface, which is settled weather. The air is descending, not much goes on. But where there are kinks going south, what we call troughs, that's where a lot of unstable air is. The air is rising very quickly, and we'll come on to that in a minute, and you get areas of low pressure. So there is a connection between what happens at, say, 8 miles and what happens at the surface. The jet stream, a fast-moving band of air, has an influence on our surface weather. So sometimes the jet stream travels very fast and what we call zonally, so there's not many kinks in the wind stream. And other times it really undulates. So let's go back to basics. Cold air to the north, warm air to the south. When the jet stream is to the north of the UK, we are under the influence more so of warmer air.
Yeah.
When the jet stream is to the south, we're under the influence of much colder air. We're on the cold side of the jet. That's what we talk about. When the jet stream is fairly straight, then what happens is the weather systems at the surface get driven by the jet stream very quickly. So the air pushes along very quickly. The weather systems move across the Atlantic very quickly. And what that means, the weather across the UK and Northwest Europe is fairly mobile. You get a weather system coming in, rain, wind, and then some sunshine. And then more rain comes in. Stronger winds for a time. So we find that during the time when the jet stream is fairly zonal, you get weather which is changeable. But then sometimes the jet stream buckles. You get a little kink in the jet stream which pushes northwards and then southwards. The winds slow, they become less strong. These weather systems at the surface then don't rattle across the world very quickly. They become slow moving as well.
Bit sluggish.
So you find you can be under an area of low pressure, which really doesn't move very far, very fast, and you get a lot of rain for a long time. Or you could be under a ridge of high pressure, which is one of the bumps going upwards, up towards the north, and we could have some fine weather. Now, in the summer, what we really like to see is the jet stream well to the north of the UK, because you get that nice, fine, warm weather. Still a bit of rain.
And we're talking about heat waves, really, aren't we? If we get this bulge of warmer air coming up towards us, it's stuck there for quite a while.
Yeah.
And it's nice and sunny.
Lovely. But then sometimes we're on the cold side of the jet in the summer, and it's quite disappointing, isn't it?
Yeah.
Like the summer of 2017, from about July onwards, when the kids broke up from school. That's where it all went a bit pear-shaped. Yeah. And other times we get stuck in a pattern which doesn't move very quickly, and that's where we can see heavy rain and flooding, when the jet stream, as I said, is buckled and doesn't propagate very quickly around the globe. And so we get stuck in a pattern, whatever it is. Now, in the summer, we like to see the jet well up towards Iceland. They can have all their bad weather, and then we get some fine weather. In the winter, if it's to the south of us, we can get a real Arctic blast, a cold blast of air, which brings snow showers, ice and frost. So we get a real sort of wintry grip of air. And in other times, the winters can be very mild if the jet stream is over us. So there's lots of variables, and the jet stream is notoriously variable. And that brings the challenges when it comes to forecasting.
This is Under the Weather, and in this episode, why does the jet stream rule our weather?
Simon, I know as well as you are obviously the ultimate weatherman in the universe, you also have a love of aeroplanes, and you like to dip into sort of the world of aviation.
Yeah.
Talk us through the jet stream and what happens when planes fly through it.
Yeah, because the jet stream, we've said it's about 6 to 9 miles high up in the atmosphere, which happens to be where commercial planes fly. They cruise at that altitude. Now, there's a very good reason why they cruise at that altitude, because they're using the jet stream. So when you're sitting there in your airplane, say going from Heathrow to New York, what you may not realise is that the pilots and the airline companies are looking really closely at where the jet streams are, and they're looking at the forecast to see where they are, because it can have a big economic impact and environmental impact. Because what they want to do is they want to try and piggyback off the jet stream. So if they're going from New York to Heathrow, the jet stream's obviously going from west to east, so they'll find where the jet stream is and they'll piggyback on it, and they'll get a tailwind, so they'll get pushed along, they'll go quicker, and that obviously will save fuel. They don't need as much of it, and time as well. We get there quicker. And I spoke to Professor Paul Williams, atmospheric scientist at the University of Reading, and I started by asking him when the jet stream became something the aviation industry paid attention to.
Well, that's a great question, Simon, because actually, I think I'm right in saying it was the aviation industry that led to the discovery of the jet stream. Of course, before planes started flying at those kind of altitudes, up to 40,000 feet, we really had very little knowledge about what the atmosphere was doing up there. We didn't have satellites in those days. Okay, maybe we were launching weather balloons, but our knowledge was very limited. It was only when planes started flying and discovered that they were arriving at their destination significantly earlier than they should have been that we realised that there was a very strong wind blowing up there, which of course we now call the jet stream.
So the planes, as we know, they go, say, from London to New York, they go slower than if they were going the opposite direction. So they're looking out for these jet streams. They're searching out what sort of equipment do they have at their fingertips to monitor this? Do they have their own specialised weather briefings, for example?
They do. Pilots and flight dispatchers and air traffic controllers are constantly keeping an eye on the weather. Meteorologists like you and Claire obviously keep very close eyes on the jet stream, but pilots are doing that too, precisely because of the tailwind that it gives to eastbound flights, and that gets them into their destination significantly sooner than they otherwise would, but also the headwinds that are presented to a westbound flight. So actually pilots are very well trained in meteorology, and they often know meteorology very well precisely because of the impacts that weather and storms and lightning and turbulence and winds can have on aircraft operations.
You mentioned their turbulence, because it's interesting that a lot of people might think, well, you're flying a plane in a wind that is more than 200 miles an hour. Do you get turbulence within the jet stream? Many of us may know, as we're coming into land at an airport, you go through some cloud, it turns a little bit bumpy. Does it get bumpy up in the jet stream?
It certainly does, and it's a different kind of turbulence that we call clear air turbulence, and that's precisely because there's no visual clue. There's no cloud that signals to the pilot that there's going to be some turbulence there. And there is a lot of turbulence in the jet stream. We think there's 3 times more clear air turbulence in the jet stream than in the other parts of the atmosphere. So one consequence of that is that eastbound transatlantic flights experience more turbulence than westbound ones, and that's because the eastbound ones try to get into the jet stream and they benefit from a very welcome tailwind, but that is where all of the turbulence is. The westbound ones try to get as far away from the jet stream as they can because they don't want the headwinds, and that tends to get them away from where most of the turbulence is.
And so is there anything that the pilots can do to look at this clear air turbulence? I guess conventional instruments may be looking at the cloud and the radar, looking at the rainfall. And obviously, if you're flying into cumulonimbus clouds, or those big towering thunder clouds, obviously you don't want to go through those because they're going to present you with a lot of turbulence. But is there anything that they can use to kind of see this turbulence?
Currently, no, there isn't. It literally comes out of the blue, often when the seatbelt sign is off and it's just clear blue skies. Passengers are moving around the cabin, so it does tend to be the kind of turbulence that has a high potential to injure people. There is some experimental technology that might come online in the coming years and decades that would allow pilots to see this clear air turbulence. The technology is currently experimental. It involves shining a laser, an ultraviolet laser, out of the front of the plane, and by looking at the reflected laser light, you can see those invisible density anomalies that indicate turbulence. Now, there are some cons to this technology. Firstly, it involves shining a laser out of the front of the plane, so there's a health and safety hazard potentially there to an oncoming plane. It's also very heavy equipment, and planes like to be as light as possible because the heavier they are, the more fuel they burn. And finally, it's very expensive technology at the moment. So we need the cost to come down, and it needs to be miniaturized. And the health and safety aspects around laser light being beamed out of the front of the plane, all of these need to be addressed. But potentially, we could see this technology being rolled out in future. I've seen some early test flight results, and it does look to be quite a promising piece of technology.
When we're forecasting the jet stream, we look at it as meteorologists. We look at the week ahead, potentially 2 weeks ahead. We can roughly see what the jet stream is doing. What sort of research is going on to look at the jet stream beyond that? Because as a tool, it's a very useful forecasting tool to see the position of the jet stream.
And airlines keep close eyes on it because they want to know how much fuel they're going to need to buy ahead on a timescale of days to weeks. It's a very hot research topic. We certainly don't understand everything that there is to know about the jet stream currently. A particular angle that's being researched quite heavily at the moment is the response of the jet stream to climate change. We have evidence that the jet stream is actually moving north at about 5 meters a day, which is
5 meters a day,
a couple of kilometers a year. Yeah. It's moving north as part of climate change, and it's also speeding up. And that's because it's driven, in simple terms, by the north to south temperature difference across the North Atlantic, for example. And that temperature difference is getting stronger as part of climate change and the spatial pattern of climate change. So we expect that to be speeding up the jet stream, and that, of course, has consequences for people's flight times as well.
Because is it the record from the US to London? That was in 2015, I think. Was it 5 hours and 16 minutes? Unless it's changed since then.
It has. That record keeps being broken.
Right, okay, there we go.
I keep close eyes on the jet stream, and I know you do too. There was a 5-day period in January 2015 when the jet stream was blowing very quickly across the North Atlantic at 250 miles an hour. And there was a British Airways flight from New York to London that took 5 hours and 16 minutes. But just a few weeks ago, a further 3 minutes was shaved off that record by a Norwegian flight, which achieved 5 hours 13. So I think we'll see more record-breakingly fast eastbound transatlantic crossings in future as climate change continues to exert its influence on the jet stream.
So if we're having stronger jet streams potentially in the future, would that also mean that the clear air turbulence that you talked about, would that increase as well because of the stronger jet stream?
Yes, that's one of our predictions. The calculations that we've done are suggesting that there could be twice or even 3 times as much severe clear air turbulence later this century on transatlantic flights. And another consequence of a stronger jet stream is that the westbound flights get slowed down even more. And this could have operational impacts on aviation too. In that 5-day period in January 2015, when the British Airways flight achieved 5 hours 13 minutes, some westbound flights in the same 5-day period were buffeted by such strong headwinds that although they took off from London Heathrow with what would normally be enough fuel to make it all the way to New York, the journey was taking so long that they decided they weren't safely going to make it to New York with the fuel that they had. So they had to stop in Maine, an unscheduled refueling stop. And again, I think we might see more episodes like that in future as well. So
potentially then more money then for the airline companies to make sure they've got enough fuel to go against those stronger the headwinds, and presumably, obviously, that's more jet fuel emissions that are going into the atmosphere.
Well, that's an interesting little feedback, isn't it? Because we all know that aviation makes a contribution to climate change. It's around the 2% level now in terms of humanity's global carbon emissions. But one way that climate change could feed back on aviation is through effects like this, changes in turbulence, planes finding it more difficult to take off on the runway if the air is too hot. Potentially sea level rise might flood some coastal airports. We expect more lightning strikes in future as well. So the impacts of climate change on aviation is, I think, going to be quite a hot research topic in future. We know very little at the moment about what those possible impacts could be.
And I guess the airlines are looking very, very closely into all of that research as well.
They are. They tend to be focused mainly on remaining profitable in the current tax year. It's quite a competitive industry, so there's a limit to how interested they are, I think, in terms of what's going on decades into the future. It's really the manufacturers, the Airbuses and the Boeings, that are keeping close tabs on that, because the planes that will be flying in the sky in the 2050s, say, the second half of this century, those planes are currently being designed, and so the designers will have to be factoring into their calculations the effects potentially of climate change. So it's not so much the airlines currently, but the manufacturers of the planes that are really keeping close tabs on this research.
Thank you for listening to Under the Weather from BBC Radio. It was presented by me, Simon King, and Claire Nazir, and was produced by Stuart Morgan and Ronan Breen.